Okay, great. So let's start. Welcome to the morning session. Today we have a full day of talks. So let's start with JJ's second lecture on loops.
Okay, so I'm going to continue pretty much where I drew it to a close yesterday. I'll remind you that I promised that by the end of these lectures, you'd be able to do a few things. What we learned yesterday is we learned how to find kinematic numerators, kinematic weights for our graphs that were dual to our color weights for the graphs, and we figured out how we could replace our color weights with kinematic weights and land on gravity, lifting linearized gauge invariance to linearized diffeomorphism invariance. So now we're going to start. We're going to look at the consequences of putting our So in order to do unitarity cuts the way I'd like to teach you to do unitarity cuts, we're going to get good at drawing graphs. We're going to get good at drawing tree graphs. We're going to figure out all the tree graphs that contribute to unordered amplitudes. It turns out there'll be a factorial number of them because that's a large number, because it grows very large. And this is traditionally why calculations have always been rather rough in engaging gravity theories. We'll see by going to a color basis, we'll find gauge invariant building blocks, ordered amplitudes. Those guys only grow exponentially. And so when we start doing cuts at the multi-loop level, we'll be able to break off small bite-sized pieces by considering ordered cuts that target very specific parts of graphs that only go after the kinematic weights, because the color weights we can trivially write down, because the propagators we can trivially write down. And then we'll be able to recycle that information to go after multi-loop gravity. Okay, so just to remind you where we are, we're writing, we're going to answer this question. What graphs? All right, so what 3-point cubic graphs contribute to an m-point tree level amplitude? By m-point, I mean m external legs. And I'll remind you that when I say amplitude here, I really mean the full amplitude, the thing that you actually square to get cross sections. So the thing that is addressed with both color and kinematics for gauge theories, or similarly, of the same level of complexity, gravity amplitudes. So what we learned last time is that for gauge theory amplitudes, like Yang-Mills, we could write things in terms of cubic graphs. We could always assign our contact terms to cubic graphs. So m-point cubic graphs. And we would dress the cubic graphs with FABCs. We sum over any repeated color indices or any internal color indices we're summing over. Those define our color weights. We've got our kinematic weights, which contain all our external polarizations, all our physical states and momenta. And then we have sort of universal propagators, right? And so this is literally what you would write down for a massless propagator, since again, we're talking about massless vectors. And if you choose an angelic representation for your kinematics, one that obeys the same color weights as your, the same algebraic relations as your color weights, you can strip off your color weights and replace them with more kinematics to get different theories. For example, you can get gravity amplitudes by replacing these color weights. So if these are Yang-Mills vectors, so if these are vector weights, then another copy of vector weights that satisfies our algebraic relations will give us predictions in gravity theories. And And we saw examples of 3 and 4 point, but in general, we're going to want to be able to go as high as we can go, as high multiplicity as we can go, and we'll recycle going far in multiplicity to going deep in loops in just a second. So let's figure out how to. So I'm going to give you a couple algorithms for generating all the graphs. But I just want to start with the simplest and one that I use all the time, which is to just start at 3 points. You won't believe how simple this algorithm is. Well, probably you already know how simple this algorithm is. You start at 3 points. You label all your edges, right? All your external edges. And then to go to 4 points, you add 4 to every edge of our 3-point graph. 3-point graph. Okay, so one example is adding it to 1. So let's just call this, let's call it our G1. And so here's our 3-point graph, and we'll just add 4 to 1. All right, what's another graph? What's another edge we could add? Oh, we could add it to 3. All right, so this was adding it to 3, and we could have added it to 2. Yeah, and this is what happens if we add it to 2. Yeah? And we're done. We've got all 3 physical channels. Guess how we're going to go to 5 points. We grab every edge in every graph, and we just add another edge. We'll add 5. So we'll add leg 5 to every edge. Let's count how many that'll be. So every one of our graphs has 4 external and now 1 internal leg, right? So we've got 5 edges to choose from. We've got 3 graphs, so we'll end up, 5 edges times 3 4-point graphs, 3 graphs gives me 15 5-point cubic graphs. And they'll all have a topology that's isomorphic to this. So this is the only tree-level 5-point cubic graph you can write down. So all 15 graphs are different labelings of this, right? Why isn't it 5 factorial, right? And says 5 factorial is much bigger than 15, because many of them are completely redundant, are completely the same as this, or the swap of a vertex with this, right? Just like rotating a vertex, like bringing this guy down or flipping these guys. And we'll consider those right now, especially for unordered graphs. We'll just consider that the same graph. We'll identify graphs by the topology, not by the order of connectivity. Okay? So for unordered graphs, we'd say this graph is the same as, which is the same as, right? So we're just going to identify all these guys. So they have the same topology, the same connectivity of edges. They have the same connectivity. Yeah? Great. Cool. So we see, I mean, the algorithm is very simple, and just by the nature of this algorithm, it's very easy to see. It's very easy to see how many graphs you have at m points, right? It's recursive, right? And you can, the easiest way to see this is there's 2m minus 3. There are 2m minus 3 edges per cubic graph. This is if m's counting your external edges. Let's check. Okay, so, well, I've got 1, 2, 3, 4, 5, right? Then I've got 5 minus 3, 2 more. Okay? Yeah? Everybody agree? Works for 4.2. Works for all points. Good. So this is the edges I have for a cubic graph. These are the ones that I get to multiply by the number of graphs I have in order to go to the next level. So if you start with if you start at m point, you'll see that there are going to be 2m minus 5 double factorial graphs at multiplicity n. Okay, so that's a lot. But it is what it is, and this, for all its frustration, it does at least make manifest where the physical factorization channels are. So, confronted by this factorial problem, right, which is genuinely there. If you want a gravity amplitude, if you want a full gauge theory amplitude, and you're going to make its locality manifest, which arguably we do at the multi-loop level. We dress graphs because we know how to integrate graphs. So we have this explosion of graphs we will be confronting, okay? But we can make our life much easier by finding minimal building blocks, the minimal amount of information that's necessary to construct these things, and then distribute that and calculate with that. So what we're going to do is yes. For all loops. So this was just a tree level counting. That's great. And so you want to know, given m external points and L loop orders, how many cubic graphs are there? I'm sure that's known. I don't know what it is. But that sounds like the type of thing the online encyclopedia of integer sequences would be all over. Okay, good. All right. So we're going to look for smaller pieces that go after the hard part of our calculation. The hard part of our calculation isn't the color weights, and it's not the propagators. It's the kinematic weights, which are specific to the theories we're talking about. So we're going to go after ordered amplitudes. And the whole key is, if you go to a color basis, go to a color basis, an independent color basis. Well, yeah, independent color basis. Every coefficient of a color basis element must be gauge invariant. And that's because once you've gone to a minimal basis in color, the color that's left are all pointing in different directions in color space. I can't cancel gauge dependence between them. They're just not speaking to each other. Yeah, good. So let's see this at 4 points. So. And I'll remind you that I'm calling this the S channel. I'm calling this the T channel. And I'm calling this the U channel. Great. And so, what color relation do we learn has to be satisfied for this thing to be gauge invariant? We learned that these color weights have to come from a Lie algebra. They have to satisfy a Jacobi relation. Right? We learned at 3-point they have to be antisymmetric. We learned at 4-point they have to satisfy Jacobi. So we can use C, T, and this is, so address these guys with FABCs. And the Jacobi identity, given these guys as labeled, is that CT equals CS minus CU. Great, so we just stick it in. And so, by virtue of these guys absolutely being independent, once we've gone to this basis, this by itself has to be gauge invariant, and this by itself has to be gauge invariant. These are what we call ordered amplitudes. We call this the 1, 2, 3, 4 ordered amplitude, and we call this the 1, 3, 2, 4 ordered amplitude. Why? Let's look at the diagrams that contribute. The diagrams that contribute to this guy are these two diagrams labeled with the same ordering. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. This contains all the graphs that share the same ordering respecting the order around vertices. This guy, let's do the same thing. 1, 3, 2, 4, and 1, 3, 2, 4. Okay. Now, for ordered amplitudes, unlike unordered amplitudes, for our graphs, we actually care about the order in which the vertices meet at an edge, because we're matching this against FABCs that have been pulled out according to a particular ordering, right? FABCs are antisymmetric. So a kinematic weight of this would come in with a minus sign relative to a kinematic weight with this flipped, right? So we're tracking that now. Good. So, well, this we absolutely recognize as what we already called our S graph. So this was our S graph. This is very easy to see. It's what we called our T graph. Great. What about this? This you have to squint your eyes a little bit, but if you're good at squinting your eyes, you can follow the ordering. Okay, so this is precisely the ordering associated with this, or you can think of it as two rotations off of it. So what I'll do is I will flip this guy up like this, so 3, 1 at the cost of 1 minus sign. And I'll flip this guy up at the cost of another minus sign. So 4, 2. Okay? Great. Now I'll rotate it so that this guy is over in this corner, and I'm dragging the 1 all the way down here. We see if I rotate it like that, the 2 is happily sitting here, and the 4 comes down precisely like this. Okay, so these guys are exactly the same graph. What about this? This is almost exactly the T graph, except this vertex has been flipped, which explains, oh my goodness, why it explains his minus sign. I was so excited. I was so excited to be writing. Yeah, so of course, if I replace CT with CS minus CU, then this NT gets dragged over to here with the minus sign, right? That was a typo, I apologize for that. But my point was that the gauge invariant objects you construct, by going into a color basis, they all share the same ordering, okay? So I'm going to tell you a simple algorithm for generating these guys. In fact, I'll tell you 3 algorithms for generating these guys, all right? Before I do that, let me make just one point relating to the duality between color and kinematics. So we can write A4 Yang-Mills as CS A. I'll just give it a Yang-Mills. You notice I'm actually trying as much as possible to differentiate a full amplitude with my curly A's and some nice rigid A's for my ordered amplitudes. So 1, 2, 3, 4. 3, 2, 4. Yang-Mills. One could imagine talking about a bi-adjoint theory. In fact, we saw at 3 points that was one of the few interesting scalar theories you could write down that wasn't completely trivial. If I had 2 pairs of F's charged in 2 different gauge groups. So these guys don't have to be the same gauge group at all, but they're going to be products of FABCs according to the structure of the graph, right? Like this, for example, could be F, A1, A2, E, F, E, A3, A4, whereas the other guy could be lowercase, just in a different group. So this would be CS twiddle, and this would be CS. Great. My point is that this guy, by virtue of the twiddle guys satisfying Jacobi as well as the C's, that I could write this as some CS twiddle A, C. Right? And what would the ordered amplitude be? This ordered amplitude, again, so for A Yang-Mills, it was NS over S plus NT over T. For, right up there, so this guy would of course be CS over S plus CT over T. This guy CU over U minus CT. Great. That means that I can write Yang-Mills as NS right? Because my kinematic weights satisfy the same Jacobi relations. Yeah? Similarly, I can write okay. Good. And this is just to emphasize the point that we will call these ordered amplitudes, ordered Yang-Mills amplitudes, like n equals 4 ordered, or n equals 4 ordered amplitudes, Yang-Mills ordered amplitudes. And sure, they show up in Yang-Mills. They also show up in gravity, right? I could have just as easily just written Yang-Mills in terms of color weight, ordered amplitudes. So, but what's interesting, and this is This is something that I'll come back to in a little bit. By even writing it like this, this is clearly gauge independent. This is clearly gauge independent. This is gauge dependent. This is gauge dependent, right? Gauge dependence here, right? Gauge dependence here. That means these guys can't be independent. The fact that I can write things like this means that my ordered amplitudes themselves must have relations between them, right? For this guy to be gauge invariant. And so and I'll talk more about that in a second. In general, for full amplitudes, we can, with this sort of adjoint double copy structure, like Yang-Mills or gravity or nonlinear sigma model, so on and so forth, we can push our full amplitude into a representation that exposes n-2 factorial ordered amplitudes. So this is our full amplitude at n point. And we're just going to sum over n-2 factorial labels. And so it'll be the color factor of something like 1, sigma 2, sigma n-1. That's n-2. So I can express my full amplitude in terms of n-2 factorial ordered amplitudes, and similarly. Right, I can do the same for gravity. This is what's called the Kleist-Coif basis. This was proven by Del Duca, Dixon, and Maltoni to be sufficient to get such a nice small basis. But as I mentioned before, just over there, the fact that I've exposed gauge dependence here means that these guys have to have more relations. So there are more relations that come from a consequence of being able to satisfy the duality between color and kinematics. All right, enough of that. Let's draw some pictures. So, right, we can't calculate if we can't identify the graphs. So, what graphs contribute to ordered amplitude? Again, we'll start with our favorite cubic guy. Okay, now we'll select all edges between 3 and 1 inclusive. Now, I said between. What do I mean by between? I mean, so inclusive is easy. It means 1 and 3 are both good edges, and any edge at a higher graph that's between them would be, to the clockwise of 3 and to the counterclockwise of 1. That's what I mean by, it's a very sharp notion, just following the uniform order around vertices. right? And I want it strictly between n and 1. Yeah? Okay. In this as drawn, in this particular way, clockwise from the n or counterclockwise from the 1. Okay? Good. I have 2 edges to choose at 3 points. So I have, graph 1, which is our S-channel graph, 1, 2, 3, 4, and we have graph 2, which is our T-channel graph. All right, 4. This is T-channel, so this is a T-channel. And 1, 2. This is our S-channel. Great. What about going to 5 points? Again, it's the same game. We're going to start at 1 and 4, and we're going to look at, for each graph, all edges between them with 1 and 4 inclusive, and add an edge. All right, so from our T channel, we've got 2 choices. We've got 1 and 4, so T1, 1, 5, 4, 3, 2, and T4, 1, 5, 4, 3, 2. And you see, by choosing the edges between, we absolutely are maintaining order, right? And we're spanning it. We will capture every graph that's cubic that has this order. So I did that. Now I just need to do the S-channel graphs. So how many choices do I have at S? I've got 1. I've got this middle guy between 1 and 4, and I've got 4. So I'll get 3 more. What does S look like? So, 1, 5, 4, 3. Then I've got this edge between, so I can go like that. 1, 5, 4, 3, 2. And then I've got branching it off of 4, so I'll drag it down. 1, 5, 4, 3, 2. Okay, so this was S1, this was S, the edge between 1 and 4, and then this was S4. Okay. Oh, good. How far back should I rewind? So what did I do? This is the T-channel graph. I called it G1, but now I'm calling it T when I'm going over here, right? I'm grabbing every edge between 1 and 4 in the T-channel graph. How many edges are there? There are 2, right? There's edge 1, right? And so that means that I've got to add some guy like that, right? Or I've got edge 4. That means I've got to add some guy like that. And so that's all I did. Why do I choose them? Because I'm going to choose all edges between m points. In this case, now it's 4. So I need to stick a 5. I need to stick a 5 in here. I need to stick a 5 in here in some way that doesn't mess up my order. If I stuck a 5 off of a 3, then there's no way that 5 will be between my 4 and my 1, right? I need to stick my 5 between my 4 and my 1 somewhere, right? And I need to orient it in the correct way, right? I need to orient it such that following, look, this is a convention. It's a convention I chose to specify what I meant by between, right? I meant by, yeah? Okay. Is that clear? Yeah? And you can see this is actually something that's very straightforward to automate. Yeah? You just find your 2 edges, and then you're just adding new edges between them. You're just navigating your graph by paying attention. So this is, I'll emphasize this very more. So this was technique 1. And it's a recursive technique, right? And it's, it's fine, it's great. And I will use this all the time. Let me just tell you something about the growth of it. And the growth of it actually tells you directly what approach number 2 should be. So this guy grows. So it's not just the algorithm. The number of ordered graphs cubic graphs. I say cubic, other people say trivalent. Cubic graphs grow as a Catalan number. In terms of the number of external edges, it's 2n minus 2 factorial. You got to include the 2 in the factorial. N minus 2 factorial, n minus 1 factorial. Maybe the number of factorials around seems spooky, but you see there's factorials upstairs and factorials downstairs, so it's not that bad. It goes exponentially. So at large n, it's very well approximated by 4n over n to 3 halves root pi. This is spectacular, so at large n. Go home, plot it for yourself. Watch the ratio between these approach 1. This isn't bad at all. This is just exponential, right? I'm saying just exponential for the rest of my life is completely factorial. Yeah? Good. Once I say Catalan number, once I say this, then especially all the geometers in the room, their ears should perk up and recall that probably Nima and Yara both talked about triangulating n-gons, right? So the other approach to getting all the cubic graphs at a given multiplicity is just find all the ways of triangulating. All right, so approach 2. Find all ways of triangulating an n-gon. Why does this work? This works because for trees, you can always go to a dual space. And dual space will, trees are by definition, you can lay out in a planar fashion, right? So you can always go to a dual space. And that dual space, when you triangulate, gives you all the cubic graphs. So at 4 points, right, I've got a box. And so I can triangulate this way, right, which gives me this graph, or I could triangulate this way, which gives me that graph. Yeah? Let's say like n-gons, 5 ways of triangulating pentagon, so on and so forth. Yeah? S&T channel. All right, great. Yes. Good, given ordered amplitude. So I did it with labels 1 through 5. Your graph labels can be whatever you want, right? They could be, right? So what would you do to get all the ordered labels to graph, A, B, C, D? Since I wrote this in the order 1 through 4, you would just take the isomorphism of, 1 goes to A, 2 goes to B, 3 goes to C, and 4 goes to D, right? And then just relabel your graphs. Yeah? Okay, good. So I assume since I didn't hit start yet, I've got 1 hour and 20 minutes to go. Is that? It's how it works with chess, right? It's still on your clock until you hit the button. Okay, good. I'm going to give you a third way, because this is going to inform a strategy I'd like to close my lectures by discussing. So this third way, that's my glare line. My third way is to use Whitehead moves. Whitehead, they're called Whitehead, sometimes they're called Jacobi moves between graphs. All right, so let's start with a graph of an order at a particular multiplicity, and we'll just focus on one edge for now. Okay, and so how am I going to write this graph? I'll write it as 1, 2, I don't know, some internal lines. I'll label this internal guy I, and so this guy from my outgoing convention is minus I. All right, so this is just a way of representing this graph while tracking the order around edges. 1, 2, I, minus I, 3, 4. Yeah? Okay, good. Now, call this G. So there is a move on an edge that leaves the rest of the graph the same, but just rearranges connectivity around an edge. Okay, and so this is called, I'm going to call it the t-hat move, and the t-hat acting on edge I of our graph will result in this connectivity. All right, so I'm going to give my internal label something different because they're no longer the same edge. You can define this edge as the connection between these two nodes, or you can talk about this edge in terms of the momentum flowing through it. Either way, that's very different than now this edge, which is connecting two different nodes. That has different momentum flowing through it. Okay, but all we did was, break apart the connectivity and reconnect. Right, and so what does this guy look like? This guy looks like 2, 3 minus j, and 4, 1 j. Okay, and so t-hat on an edge simply changes the connectivity of that edge. And this can happen deep within some graph. You just choose an edge, and then you just, it's like that childhood toy, or like gravitational waves, right? It's just like the folding like this, yeah? Good. Or, if you like, it's just changing the diagonal of your triangulation. Yes? Just one move in the diagonal, in changing your diagonalization of the n-gon. Good. So, just so this doesn't go too fast, let me do one more example. It's a great example. So at 5 points, so cubic, 3 points, there's only one topology. 4 points, there's only one topology. It's just different labels that one topology. 5 points, only one topology, different labels that one topology. 6 points is the first time you get a different topology. The way you get a different topology is actually by applying t-hat to this edge right here. Let me give it a little color. So I'm going to apply t-hat to that edge. Okay, so I'm just going to rearrange. So maybe this was an I and this was a J coming outwards. Right? I'm just going to rearrange the connectivity around whatever E and minus E is happening here. Right? And what's that going to look like? 1, 2, 3, 4, 5, 6. It's going to look like this. Okay? This is still I. This is still J. This is not E anymore. It's something different, right? It's got whatever momentum is going between 3 and 4, and it's got whatever so talking about in terms of momentum, it's 3, 4 coming through, or terms of just connectivity between nodes, right? 3, 4 coming together is a different node than this. I, J coming together is a different node than this, so it's just a different edge. You can call it whatever you want. F and minus F or something. Good. What do we notice about the t-hat the t-hat, the Whitehead move, Jacobi, the t-hat Jacobi move, it preserves planarity. It preserves color order. T-hat preserves great. So recipe 3, you get ordered graphs. You start with a graph of the correct order and multiplicity. And apply t-hat to all edges. And then all edges of all graphs you get, and so on until closure. All right, so what's a great graph to start with? You can always start with what we call the half ladder graph. We call it a half ladder graph because if you flip it up and join it, then you've got a ladder. Right? You can start with the half ladder graph, sometimes called the multi-peripheral graph. That is easy to make sure it's got the order you want. Right, and you just apply t-hat to all edges in this, and then all edges and all graphs you get out, and also until you're not getting any new edges, until you've closed, right? Until you've got a set that just closes in among itself under applying t-hat. In the graph of graphs, I'll just say it. I won't write on the board. Yeah, I won't write on the board right now. In the graph of graphs, that gives you the one skeleton of a polytope called the Associahedron, right? Just applying t-hat till closure. Of course, it has no geometry until you give those graphs some sort of coordinates, right? And so choosing the coordinates, right, you can come up with, it turns out for Associahedron, for these guys, you can get a polytope, you can get an Associahedron. And you can relate that Associahedron to the actual amplitudes of special theories, as Nima was talking about. I want to talk about one more Whitehead move, and perhaps the hint is the fact that I could also have called it a Jacobi move, and that's U-hat. That's too high. U-hat, right? And what does that do? So a U-hat on I on our graph results in this connectivity. Okay. As is hopefully obvious by the name, but I don't know what I call this. They'll call this L and minus L. And so what does this look like? 3, 1 minus L, L, 4, 2. Okay. Right. Again, you can do this within a graph. The interesting thing about starting with a half ladder and applying U-hat on all edges is you'll only get half ladders back. You'll always only get half ladders back. It turns out that forms, so U-hat till closure on the half ladder gives a one skeleton of another polytope called the Permutahedron. It turns out that polytope, or if you like, all the half ladders with the dangly legs fixed, fix them at 1 and n. All the half ladders, what does that give you? That gives you all permutations of these guys. right? That serves as a basis at any given multiplicity via Jacobi to generate all the other graphs, right? So all 2n minus 5 double factorial graphs you can get from the n minus 2 factorial graphs of the Permutahedra via Jacobi. All right. I want to get to loops, but while we're here, let me just emphasize a couple points while looking at the graph of graphs, because this will make my life easier in a second. So at 4 points, we start with an S-channel graph, apply t hat, get a t-channel graph, apply a u hat, get a u-channel graph. All right, so I'm drawing a graph of graphs. Every node is a graph. Every edge is a whitehead move that gets me between them. There's actually, so this was a t hat. This is a u hat. If I want to go from here to here, there is a whitehead move. I'll call it a t bar hat. And it's like a t hat, except you flip one of the edges, right? Incurring sort of a minus sign, right? As we do before. Anyway, so in this graph of graphs, every edge is an at 4 points, every edge is an associahedron, or a color-ordered amplitude, right? Only when you bring all the graphs together do you get a full color-dressed amplitude. You dress it with all the color weights, kinematic weights, and propagators. What I will say is every time you see a triangle in a graph of graphs, triangles are an occasion for a Jacobi relation. Which means if I know any two of the vertices of the triangle, then I know the third via Jacobi. Okay? Good. Let's look at all the 15 graphs that contribute to 5 points. So, okay, so this outer guy, this boundary data, if you like, is, again, I keep 1 and 5 fixed, right? Then I apply u hat, so I'm applying u hat, right, to go through my graph till closure. I get 6, right? So this is a Permutahedra of 5 points. I have a Jacobi relation between any two of these. It takes me inward. Right? So if you like, it's t hat operations on either this edge or this edge. T hat on this edge brings me up to here. A t hat on this edge brings me up to here. All right, so this is a t hat on, A, and this is a t hat on B. Okay? So I add 6. I've got 6 again, right? And it turns out that's all that's left are 3 more. Okay, and these guys are all related. Okay, good. I drew it. It's pretty, and it's kind of fun. One reason I'm drawing this is because it will allow me to visually make a point about the relationships between ordered amplitudes. So what does an ordered amplitude look like? Again, so an ordered amplitude would be applying S hat till closure. So let's applying T hat till closure. So this is 1, 2, 3, 4, 5. Right, I apply T hat on this. And what does this guy look like? So I'm bringing 2 and 3 out like this. 2 and 3, then 1, 2, 3, 4, and 5 are still connected like that. Now I could apply a t hat on this guy, and so I'd have 2, 3, 4, 5, 1, and so on and so forth. Yeah? But what do I have? I have an ordered amplitude. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so on. Yes? Great. So it's an ordered amplitude. You might think that you need 6 ordered amplitudes to fully constrain the 5-point full amplitude, right? This would be the basis, this would be the Kleist-Coif basis of n minus 2 factorial, right? Yeah? That's what you need to touch every graph. But it turns out that's not, that's not what you need. In fact, you only need 2 color-ordered amplitudes . 2 ordered amplitudes. That's sufficient to get all the boundary data. And then all the rest follow from Jacobi coming in or relations between the ordered amplitudes. I'm gonna get to loops right now, but I'm gonna finish this point because it minimizes the number of ordered cuts we need to do to constrain the full amplitude. Okay, so I just want to explain that. Ordered amplitudes have lots of properties. And you can understand all these properties once you look at the graphs that are inside them, right? One that's hopefully very obvious is they're cyclic. Yeah? Right, I mean, that should be obvious from this picture, right? This is a rotation. There's a rotation in this picture, yeah? 2, they've got a reflection identity, which is that A, 1, 2, n equals minus 1, n, A, n minus 1, 1. Okay. This is easier to see when you actually just look at the cubic structure of graphs. Anything that's going to have an even multiplicity, flipping like this doesn't incur a sign. But if I flip over something with an odd multiplicity, then I've incurred a sign around that vertex. Okay? Yeah? Good. There's the Kleist-Coif relations that let us express everything in terms of, so, you know, any graph, whatever. So since it's cyclic, I can write like 1 sigma. I can write in terms of some constant, some number. It's going to be +1, -1 is 0. Sigma rho A 1 rho n. So I can always go to this n minus 2 factorial basis that I wrote earlier, right? And what's sitting out in front of the kinematic weights are the color weights of the half ladder that defines this order, as I wrote before. Okay, and then there are these n minus 3 factorial relations that you get from Jacobi that actually allow that actually force these guys into a further basis. So if I'm awkward around the so a lot of people call these the BCJ relations. I like calling them n minus 3 factorial relations. So these guys, again, now it's going to be functions, rational functions of Mandelstam variables where you fix. So this is going to be over S n minus 3 factorial. S n minus 2, right? So you fix 3 legs. It's not hard. It's not hard to find these relations, right? Once you know that the Jacobi relations exist, then it's just a pseudo inversion of the relationship between ordered amplitudes and the kinematic weights. So I'll just make this point really quickly. 1, 3, 2, 4. Let's say A1, 3, 4, 2. Okay, good. So I wrote down three different ordered amplitudes, where I've got my ones here, and then they're not related by reflection. Okay, 3 different ordered amplitudes. Of course, they're by no means independent. You can see right away that if I add them together, I get 0. So they've got to be dependent. Yeah, and in fact, that dependence are the Kleist-Coif relations, right? And that comes from the fact, ultimately, that that your color weights satisfy Jacobian antisymmetry. So color weights satisfy Jacobi. Okay. But there are more relations between these that only become, so I should remind you that S plus T plus U equals 0. But the fact that NS equals NT plus NU forces further restraints on these guys. Okay? What it ends up forcing is that A 1, 2, 3, 4 over U equals A 1, 3, 2, 4 over S, A 1, 3, 4, 2 over T. These guys are all exactly the same. All right, so there's in fact only one independent ordered amplitude, which is 4 minus 3, right? Good, at 4 points. Is there anything more I want to say about this right now? There's another consequence to this. Okay, but sorry. So I didn't do the arithmetic, but you can do the arithmetic, right? You just plug this in, and you try to solve for your n's in terms of your a. Oh, that'd be great. Wouldn't it be great to just be able to write my Jacobi-satisfying numerators in terms of my amplitudes? Turns out there's a singularity, so you can't invert it, and it's because these guys are actually related, right? That doesn't mean that you can't express your n's as functions of a's. They become non-local. You can do it functionally, but that'll take us afield from where I want to go. Other than if you solve for your n's in terms of your a's, right? You'll get something. Well, let's just whatever. I don't want to do it right now. But if you solve for your n's in terms of your a's, you can stick those n's into the double copy relation, and you'll get a relationship that's just between ordered amplitudes. And all generalized gauge dependence drops out. All right, so whatever, we've got some Right? So you get some expression ng is some over some ordered amplitudes, and there'll be some residual gauge freedom, left some additional n dependence that won't drop out. But when you stick it in the double copy, right? So let's say you've got some ordered amplitude, and I'll just write it like this. So A cross B. So what do I mean? I mean I've got some A of G, some B of G over the denominator. This will turn into a relationship just between ordered amplitudes. Okay, and this kernel is known as the KLT kernel or the momentum kernel. This was first seen in string theory where these guys were color stripped, so color ordered open string amplitudes. And these were color stripped open string amplitudes, and this had all sorts of alpha prime dependence. And so you got out closed strings by sums over permutations of ordered products of permutations of ordered amplitudes times all these sine functions and stuff like that. And so this was known from quite a long time in the 80s, right? And so when people first started trying to get sharper calculations at higher loop orders in the 90s, they took the alpha prime goes to zero limit of these guys and got a field theory kernel. And so V. Byrne and Lance Dixon and collaborators wrote down the full all multiplicity expression for this kernel that would mix up different orders of ordered amplitudes and combine it to get gravity for Yang-Mills. Anyway, that's an aside, but I just wanted to point out that this actually makes this is written purely in terms of gauge invariant quantities. It's harder to generalize at loop level and stuff that's nice and local in terms of graphs like this. This generalizes very easily at loop level, but it's got all sorts of features too. All right. Let me get to some loops. So what we saw last time is that I can bootstrap my way up to all multiplicity tree level, starting with 3 points, imposing symmetries like gauge invariance, imposing factorization, right? And for if I know everything I want to know about my theory and I can impose it, then I'll have no freedom, right? But and so you can construct Yang-Mills to all multiplicity just by, for example, imposing gauge invariance and factorization, or the duality between color and kinematics and factorization, multiplicity by multiplicity, and you will uniquely correctly get Yang-Mills. And you can do the same thing to go after loops, full color-dressed loop integrands. Now, we heard an excellent discussion by Yara. I think it was your first lecture where he talked about that there was no the integrand for a non-planar, or at least no finite the integrand for non-planar graphs, and that's true. That's true. There's a problem. It's called the label shifting problem by some people, and what that means is that sure. I mean, there's an integrand in the sense that I can absolutely talk about L loops in a non-planar theory. Whatever d L1 through d L d d, right? Whatever norm. Some expression. right? That gives me my L loop amplitude. There is something that's sitting under an integrand, right? But the point is, it's not unique, and it hides factorization channels. And that's the real problem. The real problem is any expression you write like this, there are some cuts that are hard, if not impossible to see, by multiplying by channels and then taking the limit of those channels goes to 0, just because I haven't written that order in that way. Okay, so that is a barrier to the integrand. So we're going to define an integrand operationally in something that we can use, and as long as it satisfies the right criteria, it will integrate to the correct thing. And so that's what we're going after. So our integrand, and this is something you can use for planar and non-planar. It can, Lorentz violating, all sorts of stuff, right? Anything you want. It's a mapping from canonically ordered graphs to kinematic weights. If there's color weights, propagators. Say L loop graphs with the following properties. Mappings are automorphic symmetric. So that the dressing doesn't care when I want to dress a particular labeling. It doesn't care which isomorphism I took from the canonically labeled graph. That's critical. That's what allows us to proceed. Yeah, and that's what we need. I mean, that's really what we need to define an integrand, and then this integrand is appropriate for our theory if it satisfies all cuts. Okay, and so this is what allows us to verify integrands. So Yara hands me his favorite integrand for whatever theory. I can check it. I can check that the integrand satisfies the cuts. It satisfies the cuts, then I know it's a theory I'm talking about. So this is a cuts in terms of physical channels of what particles exist in the theory. This is a very, very strong constraint. It is stronger than we need. What we could get away with is any cuts that are not satisfied in a way such that they integrate to 0. Right? We could get away with that, but we don't. That's harder to work with. It's far easier to work with something that's stronger, and we can go really far with this, building expressions that are automorphic symmetric, and they're automorphic. We can just check that they satisfy all cuts. Now, as we've seen, there are a factorial number of graphs going out in multiplicity, and if you bring them back around to sew together to get loops, that's a huge number of graphs. So all cuts sounds expensive. And if you had to check each cut, that would be more trouble than it's worth. But cuts span. If I can get cut B from applying cut conditions, to cut A, then A spans B. And what do I mean by A spans B? I mean, if my integrand satisfies cut A, it will automatically satisfy all cuts that I can get by cutting cut A. Which means to verify the cuts, all I need to do is start with my cubic graph, start collapsing propagators until I get a very small number of cuts in terms of large trees. And I do the small number of cuts, and I can verify an integrand. Easy verification leads to natural construction. So if all I need to do is satisfy the cuts, why don't I just start from cutting all the propagators, assign that obligatory data to every cubic graph, and then see what data am I missing? Because that data has to be there. I can't have made any mistakes as to what I've assigned, but I could be missing things that were zero under those cut conditions, things that were proportional to inverse propagator squared, right? And what you can do is then release cut conditions. Consider cuts that are almost maximal, except for, now I include a 4-point tree instead of just 3-point trees. If I'm doing ordered cuts, so I'm going to make this point really sharp. So let's say I'm talking about 3 loops. All right, so I can consider a maximal cut of this graph. So I'm putting every internal leg on shell, and that data has to be associated with this graph. Okay, but what could I be missing? I could be missing stuff that's proportional to this loop momenta squared, right? Because I assign things under, sewing a bunch of 3-point trees together. So this vanished, L squared is 0. I could be missing this, but I will definitely see such a contribution if I now consider this cut where I'm now sewing in a 4 tree. Yeah? So what was an exposed L that was set to 0 is now completely off shell in this cut. And so if I should have been assigning it to this graph, then I'll see that I'm not satisfying this cut with my current assignations. And I can assign that data to any of the graphs that can contribute to this cut. Okay, and if I'm talking about ordered cuts, there are only 2 graphs. Only 2 graphs contribute to a 4-point ordered cut. There's this guy, which was this, and then there's this guy, which is that guy, right? Which is just this guy relabeled. Yeah? So I already know what its maximal cut contributions have to be, right? And so with just this one cut, I can see whether or not I'm missing anything that is loop dependent here, right? And so you just keep rolling up and up and up. And it has to stop because there are only so many derivatives in any theory. Yeah, so there's only so much loop momentum that could ever be upstairs. And that sets, for any given theory, the maximal number of off-shell propagators you need to include in cuts in order to verify the theory. Or sorry, in order to construct the theory. Then you can always verify on some, some big spanning set of cuts. Okay. Yara, how much time do I have? Am I at the boundary, or do I have 5 minutes? I have 5 minutes? Okay, good. I'm going to take the 5 minutes. And I'm going to take this 5 minutes to just tease an algorithm for you that will let you push data from a well-known sector to a less-known sector. And this is the way I want to do it. So I'm gonna draw all the graphs, all the planar graphs that contribute to n equals 4 super Yang-Mills. Okay. At 3 loops. Now, these are just the topologies. Of course, what's actually in the integrand are all the ways of relabeling this consistent with planarity, right? Yeah. But only these 2 topologies contribute, right? So when you actually want to integrate, you got to draw all the topologies and all the labeling, right? Good. There are a bunch of other cuts. There are a bunch of other graphs that contribute to the full n equals 4 super Yang-Mills theory. The nice thing about n equals 4 you never need triangles. You never need triangles, and you never need bubbles, and you never need tadpoles. Which means that that even though 3 loops, it's a lot of loops, there's not so many cubic topologies that contribute. You can get everybody in terms of 9 graphs. Right? So what will some of the graphs look like? They'll look like. Yeah, stuff like this, right? They'll start to contribute. Or, stuff like that. That'll start to contribute. I'm not going to draw all the graphs, but these are some of my favorite ones. And these guys, when we first went after 3 loops in n equals 8 supergravity, these were definitely the most annoying guys in Yang-Mills to come up with, and then they were the most frustrating to address with supergravity, because this was before we understood double copy the way we do now. But my point, okay, good, so whatever. So 2 graphs, you've got 9 graphs, so you've got 7 non-planar graphs. They'll look like this in friends. It turns out that at 3 loops, just by knowing the planar graphs exactly, so just by doing planar cuts, you can completely constrain the planar graphs, or you can ask your Amplituhedron to tell you what the planar graphs are. We heard from, or your Correlators, we heard from our friend earlier this week that they've got 11 points at 4 loops. 11 loops at 4 points for n equals 4 super Yang-Mills in the planar sector. Soon they're going to have 12, right? So the planar sector is bananas well known. And so you can ask yourself, let's say I want to go after 7 loops in n equals 8 supergravity, or 8 loops in n equals 8 supergravity. How can I get the non-planar sector given this knowledge? And how can I get it in a way that's usable? Because at the end of the day, we want to do as little work as possible. And what I want to emphasize is that you can absolutely use field theory relations to recycle the data you've assigned to this cubic graph, this cubic 3-loop planar graph, to get this guy, this guy, and this guy. Right, so this data that you have in this graph, you can recycle using tree-level relations I talked about earlier on cuts. And I'll draw the cuts and I'll go through one example very quickly. And it turns out that this guy is enough to get these 3 graphs, and this guy is enough to get the other 4 graphs. So you can get the entire non-planar amplitude from just the planar sector at 3 loops, and then turn it into gravity trivially. So here's the cut that gets you this guy. Here's a cut that gets you this guy. And here's the cut that gets you this guy. So it informs this, and this informs this, and this informs this. And what you can see is there is one ordering where the only graph that contributes to this cut is one ordering of this guy, this topology, where I'll do it right over here. So if my ordering around this is, 1, 2, 3, 4, like this, then I have a contribution that looks like this and a contribution that looks like this, which means in the context of where that is on this cut, I have this guy, or I have this guy, right? Just from blowing up that cut. Yeah? Right? Good. With this ordering. But this guy has a triangle, and we've assigned it 0 in the planar sector. So the entire cut just comes from knowing this, right? And so we can call that the 1, 2, 3, 4 ordering. But we know that there is a 1, 3, 2, 4 ordering that equals, quite literally, this divided by this. So 1, 2, 3, 4 divided by u times s. So s over u times this guy equals this, from the 4-point relations we wrote down before. Yeah? Good. What graphs contribute to this? This was just our U channel and this guy. So what we have is minus our 0 plus this guy. So this guy equals this guy with this ratio under cut conditions, right? And so you can just push out from this guy to this guy on those cut conditions and keep tiling outwards data. Now, you might be missing things that, that were proportional to loop momenta, right? In which case, it will be informed by other planar cuts, planar dominated cuts. Then you can verify at the end when you start considering this cut, which is entirely planar dominated and touches all the graphs in all the ways. All right, so with that, I think I'm going to conclude my lecture, and I hope some of you, all of you, decide to start looking at higher loops in gravity theories.
Okay, big applause to JJ for great lectures. We are a little over time, but if there are any questions, comments. Actually, I have one, but it might be a little harder to answer. So one thing which has been always bugging me is this graph automorphism. Like more the fact that the same diagram contributes multiple times on the given cut. You have to find the paths through the diagram. So this is avoided for planar diagrams if you really label your loops distinguished, that this is L1, L2, L3, then this never happens. But we cannot do it consistently for non-planar because of the absence of the integrand, so then this happens. Do you think it's the same issue as the labeling issue, or it's something has to do with non-planar topologies, even ignoring the labels themselves?
Well, so good.
Feel free to give short answer now.
Yeah. So what I will say is we can always back away from complete automorphism symmetry if you, at the cost of introducing more graphs, right? And so we can, so we can achieve an integrand that functions exactly like the planar integrand in terms of, for the planar sector certainly, in terms of never having the same labeled graph contribute multiple times to the same cut, right? So we can do that, but in terms of as efficiently as possible capturing all the data, all the independent data that's in a loop amplitude, that seems more expensive. And I haven't seen the benefit of using it, but I'm very open to being sold on it. As you know, a long time ago, I entertained the maximally asymmetric graph representations for loop level. And it's fun because you can do a lot of things at loops the same way you can at trees, but at a certain point, you're just drowning in graphs. And so, yeah. I don't know if that was a short answer.
Sure, perfect.
Yeah.
Okay, more questions. Do you have microphone around or?
Hello.
Hey.
You showed the double copy method for, let's say, 4 graviton, and from 4 graviton amplitude, you can go to 4 gluon amplitude, you can go to 4 graviton amplitude. So now let's say I have the situation where I need 2 massive spin 1 particle and 2 gluon amplitude. From there, I want to get 2 massive spin 1, 2 graviton.
All right, I'm going to repeat your question. I suspect we may want to take this offline, but let's do. Okay. I'll see if I can do this quickly. Okay. Because we're standing in the way of coffee. So you want massive particles?
Yes.
Like massive scalars or massive vectors? Which do you want?
Massive vector.
You want massive vectors?
Yes.
Okay. Good. All right, and you want massive vectors. Yeah, so you want massive vectors coupled to gravity.
Yes.
Yeah, great, easy, no problem. Okay, so how do you get massive vectors coupled to gravity? You can do it with massive fermions coupled to glue, right? So you can do it with quarks.
Okay.
Right. So this is spin 1/2, spin 1/2. This is spin 1, right? And so this I can literally square to get whatever, spin 1, And this is a graviton exchange. Spin 2.
Okay.
Yeah. Now, at tree level, because they have mass, literally squaring will introduce a dilaton you need to project out, right? But that's incredibly systematic. It's a systematic to project it out on cuts if you want, which is trivial and automatable. There's also clever ways of adding wrong sign matter to this theory that projects it out. Projects out the dilaton exactly. Now, let's say you wanted to be talking about, massive spin S, because you've got Kerr black holes and they're not kind enough to be just spinning at 1 in whatever quantum units, right? So they're going to be spinning at some gigantically large thing. So you're going to ask me, can I get to those arbitrarily massive spin blah with double copy? So you absolutely have every right to be talking about them in terms of scattering amplitudes. We can absolutely construct the 3-point amplitudes trivially by composing spin ad infinitum, right? And so, and you can preserve gauge. What I'm going to say is that there are open questions with very, very high massive spin coupled to glue, turning that into very high massive spin coupled to gravity. But I suspect that there's a path forward in it. So, but I haven't worked on that particularly. I can give you references for people who are actively working.
Maybe we can talk over coffee.
Awesome.
Let's go to coffee. Thanks a lot, JJ, again.
Sure. Yes.